Hey, this is Mr. Vale's math class, and I'm going to show you the different notations for derivatives and how some of them end up getting used in different situations. So, if we're going to be taking the derivative of a function, we need a function. So what we're going to start out with is our function y, which is equal to f of x. I could have chose something like g of t, where g is your function and t is your input, but I decided to choose x because we use x a lot, and I decided to use f for our function notation because that's a common notation. So, common ways to notate derivatives. The first one, and probably the most common, is using a prime symbol, or y, the first derivative of y, like that. Another one is they'll write dy over dx, or what this means is the change in y with respect to x, which is kind of a version of rise over run. So y is your change in up and down, over run, which is your change in left and right. The next one I'll show you is, this is very similar to the last one, but it's d dx of y. And a lot of times this notation gets used to show that you are taking the derivative of something. This one also gets used like that, but this is typically clear. And this one is typically shown to show that a function is a derivative. So they'd say this is equal to something. Now figure out what your initial function is. That's what gets used a lot for that. So the other way to notate derivatives is using this notation function. It's very similar to the previous one, but essentially it would be like with this notation, it would be f prime of x, like that. Or it could be written df of dx. So they don't include the x there because it's assumed by the bottom part, or you're changing f with respect to x. And then the last one is very similar, but it is d dx, or taking the derivative of f of x. So that is another notation. Now, this is for the function of the derivative. Now, if we just want the value of the derivative at a specific point, you'll notate it like this. So df, or the change in f with respect to x, at or such that x is equal to a. And that would be the same thing as if we said the derivative of f at a point a, where a is a number that's on your domain, or like can be an x value. So that would be the derivative at a specific point. Now, let's see what some applications would look like. One common application, or one that's kind of easy to conceptualize, is, let's say we're doing miles per hour. For miles, we'll use an m, and for hour, we'll use time. So if I was gonna notate this, I would say change in miles, or dm, over dt. So let's say we're going 30 miles an hour, then our change in miles over change in time is equal to 30. Another version for rate is, let's say we have something like a weird shaped vase. We're pouring water into this, and over time that water goes up. So we could say the height at which the water is at, so dh, is changing with respect to time, dt, as some liquid gets poured at a consistent rate into this. Another way you could look at it is, as the height goes up, the volume changes. So as the height is going up here, the volume is kind of increasing quickly. Right here, even though the height's going up at the same rate, the volume is actually increasing more slowly. So as the height changes, the increase in volume also changes. So the change in volume can be related to the change in height. And then the cool thing is, let's say if height's related to time and volume is related to height, you can actually combine these two rates and relate the volume to the time. So this water is being poured in at a consistent rate, and over time, the volume is changing of how much is filled in. So that's another interesting way you can kind of create rates that exist in real world situations. It's not always just dy dx, you know?
In Mr. Vale's class.
Very nice.